Hi everyone. So this particular video is going to complete the section that we talked about in lecture yesterday, but didn't have time to do a couple of examples, and then some other videos. The next few videos will cover the new topics. So where we ended our discussion yesterday was on this bit about center of mass. So we're looking at applications of double integral. The next application we have is a moment of inertia. And moment of inertia is a concept from physics, and it's basically inertia, as you know, means resistance. It's used to measure the resistance to rotational motion or rotational forces that cause rotational motion. And we won't go into very specific details about these. We're going to look at what the expressions are. There are three kinds of moments of inertia we will consider, about the x-axis, about y-axis, and about origin. Now you may wonder why we have all these different things. What you can do is simply consider an object around you, like a cylinder. It will have different kinds of resistance to rotation in one axis as opposed to other axis, and that's basically why we have different formulas as well as different expressions for moment of inertia. Now if you consider something like a sphere, of course all of the moments will be the same because it has symmetry in all directions. So about the x-axis, so what we have is, as with the center of mass, we have the density function for a given object, and the moment of inertia about the x-axis, also written as I sub x, is given by the double integral over the region D. We multiply it by y squared. We multiply the density function by y squared and take the double integral. So when it's about the x-axis, the moment is described by the distance from y, so y squared. And when it's about the y-axis, the moment takes into consideration the distance x from the x-axis, so it's x squared rho xy, which is your density function dA. And if it is about the origin, also written as I naught or I o or I zero, is the double integral over the same region, but in this case we are going to add the effects of x squared plus y squared rho xy dA. Okay. Now if you notice, this x squared plus y squared in polar form is just r squared. So there is something there going on with the moment of inertia around origin, where we're taking this distance from the origin, and distance from the origin is r squared, which is x squared plus y squared, which is why this is also called the polar moment of inertia. Okay, so you can identify this x squared plus y squared as r squared. Let's look at an example of what a problem might look like. So suppose there's a homogeneous disk D with density function given by rho, so it's constant. The center is at the origin and the radius is a. And we want to find all of these ix, iy, and I0. Okay, so what is this disk? A disk is some circular thing that has width. A homogeneous disk means it has a uniform or a constant weight distribution. So it means it's just evenly distributed. You can think of it like a plate of weight on the gym or something. They usually have constant distribution, and we are attaching a coordinate system to it, and we are saying this is the center and the radius is a. So if we simply look at ix, that's going to be double integral over this disk y squared times constant times dA. And to evaluate this, because the boundary is circular, right? So the base that we are working with is circular, and whenever we have something circular, means we will use polar method. So if we use polar method here, first let's look at the limits. The radius goes from 0 to a, and we make one full circle. So this is 0 to 2 pi. The rho is a constant, it can be pulled out. Y is r sine theta, so this becomes r sine theta whole squared, and we have that additional r for polar coordinates. So this simply becomes, this is separable, right? So I can write this as rho, or let's do it one at a time. So we get r cubed sine squared theta, right, going from 0 to a, and a dr d theta. So first, doing the integration with respect to r is going to give me r to the 4 over 4, which becomes a to the 4 over 4 when I plug it in. And then I will have a 0 to 2 pi sine squared theta d theta. And we know how to work with sine squared theta. We're going to write that as 1/2 of 1 minus cosine 2 theta. And if you work through this, you're going to get a pi over there. So this eventually is going to become pi rho a to the 4 divided by 4. Something similar will happen when you find Iy. You have x squared rho dA, and once again, since the boundary is circular, we will use polar coordinates. These limits will be the same. The only difference is you will have a cosine instead of a sine, which means, well, the next step also looks pretty much the same. The only difference is one of the integrals is now cosine squared instead of sine squared. So this becomes rho a to the 4 over 4, 0 to 2 pi cosine squared theta d theta, and which also will give you the same result because you will use the half angle formula, and this will come out to be pi. So you are left with. So if you consider, if you look at this plane, right, the x and y plane right here, whether you rotate it in the x plane or in the y plane, in this particular case, it has the same inertia. Okay, because it is symmetric. Now, if you look at I naught, and it's x squared plus y squared, right, rho dA over the region D, but since integrals can be split, this is really just x squared plus y squared rho dA, which means it's ix plus iy. So it's pi rho a to the power over 4 plus pi rho a to the power 4 over 4, which becomes pi rho a squared over, oh, that's wrong, a to the 4, but divided by 2. Okay, so the moment of inertia, the polar moment of inertia, is half of all of these. Okay, so that becomes your result for your moment of inertia. Okay, the last application that we will briefly look at is probability. We won't be spending too much time on this. So probability, briefly sort of revisiting what you know, it's the likelihood of a particular event in a sample space to happen. It takes values between 0 and 1. If something has a probability of 0, it means it's impossible or to happen. If it takes a probability of 1, it will certainly happen. And it takes all values in between. But actually, when we consider probability, it's usually a distribution. So when we talk about how likely is this going to happen, there's a distribution that is associated with it. And so what we have is it's called, so if f is a probability distribution function, basically how integrals come into play is that if f is a probability distribution function, then if you take the integration, if you take all of these probability from negative infinity to infinity, they need to add up to 1. So this is the condition that is satisfied by every probability distribution function. So if you take the integral from negative infinity to infinity, it's going to be 1. What that means is if you add up all the probabilities, it should come out to be 1. And the probability between a and b similarly is given by a to b f of x dx. So what's happening here is, here's a probability distribution. If you want to find the probability of something between a and b, then it amounts to finding this area, and that amounts to finding this integral. So where does double integral come in? The double integral comes in when you have something called a joint density function. So joint density function is when we have a pair of random variables x and y. So in this case, the probability is given by the double integral in the region D of the joint density, which is fxy, over the region D. So here x comma y belongs to some region D. Okay, and basically if your region is a rectangle, then it's just similar to finding double integrals over a region that is rectangular. Let's look at an example. Suppose the joint density function is given by xy c x plus 2y if x is between 0 and 10 and y is between 0 and 10 and 0 otherwise. So what is this saying? Let's take a moment to understand what this is saying. Well, c is a constant, and it says find the constant c, then find the probability of x less than 7 and y greater than 2. So this is saying x and y, suppose these are two things that are happening, right? And as long as x takes values between 0 and 10 and y also takes value between 0 and 10, there is some chance of it happening. And what's the chance? The chance is given by c times x plus 2y. But if x takes the value outside of 10 or 0 and so does y, then the probability is 0. So meaning that cannot happen. Okay, so the first thing we got to do is we got to find c. To find c, we will use the fact that when you add up all the probabilities, you should get 1, because even for a joint probability scenario, that holds. So solution, to find c, we use the fact that the double integral of f, right, over r squared equals 1. So really what we're saying is, if we go all the way from negative infinity to infinity for both, so it's a huge region, right? But remember when we did 15.2 where it was integration over double integral over general region, we do something like this, right? We make a step function and we make a compound function, and we make value 0 outside of the region. So we create a rectangle. So here, this will simply reduce to 0 to 10 and another 0 to 10, c times x plus 2y dy dx, and that's because outside of the 0 comma 10 cross 0 comma 10 rectangle, f is 0. So we're just adding a bunch of zeros, so it doesn't matter. We don't have to take that into consideration. All right, so now this can be worked out because c is just a constant. Let's take the derivative with respect to y. I have 0, 10. Sorry, not derivative, integral. This becomes cx y plus y squared. Plug that in. Now it's integral 0 to 10. You have 10 cx plus 100. Then 0 to 10, and that is 10 cx squared over 2 plus 100x. Looks like I made a mistake here. There's a c is distributed to both, so there will be a c here and then a c here and then a c here. Okay, so that's 5 times 100 is 500, so 500c plus 1000c is 1500c. All of this needs to equal 1, so 1500c equals 1. That gives me the value of the constant. So now I have the actual distribution, right? And if I want to find the probability of x less than 7, y greater than 2, I have my c, which is 1 over 1500, and I have my distribution function, x plus 2y dy dx. All I need to determine now are the limits of the integral. To do that, I'll look at y first. Y goes from 2 is greater than 2, so it goes from 2 to infinity. And x is less than 7, so it starts at negative infinity and ends at 7. But outside this box of 0 to 10, our probability is 0. So it really reduces to, I only need to consider from 0 to 7 and then 2 to 10 of 1 over 1500 x plus 2y dy dx. And this one you can evaluate, right? Pull out the 1500. First, with xy, you get xy plus y squared, 2 to 10, 0 to 7 dx. What does that become? That's 1 over 1500, integral 0 to 7, 10x. Oh, that's not correct. It's not 0, it's 2 to 10. So 10x minus 2x is 8x plus 96, 100 minus 4, 1 over 1500. That's going to be 4x squared plus 96x, 0 to 7. So 1 over 1500, 4 times 49, so that would be 196, and 96 times 7, so that's 700 minus 28, so that would be 672. So you get what's that, 700 up top, and then 4 short of 72, 68, so 868 over 1500, which will be, you can find this as a decimal, and it should come out to be less than 1, right? It should be between 0 and 1 because that's a probability. That's the chances that whatever this x is less than 7 and y is greater than 2, given that this is the probability, the joint probability distribution for these events x and y. Okay, so those were the 2 other applications that we did not cover in class. And the other topics for this week, which we cannot cover in lecture because tomorrow is a holiday, will be done in the subsequent videos. All right, that's it for this particular video.